I am Binita Hazarika from Lakhimpur Girls' College. And now, dear participants, at the very outset, I would like to welcome you all to our college and the 3-day international webinar, Recent Aspects in Physics. The webinar is organized by the Department of Physics, Lakhimpur Girls' College, Assam. Dear all, we are in a very hard time now. The whole world is under the pressure of COVID-19 pandemic and we all are away from classroom teaching. But technology allows us to gather like this, and to some extent we are able to stay at our track. Now I'd like to introduce today's resource person, Ishwita Saikia, in front of you. Ishwita Saikia is a very young physicist. Her parental home address is our hometown, North Lakhimpur. Permanent address is in Ahmedabad, and current address is 601E University BLV Unit 108, Dallas, Texas. She completed her bachelor degree and master's in physics from Delhi University, recipient of Golden Jubilee Award 2012, Best Student in Science Department. Currently, she is a PhD research scholar and now at Southern Methodist University, Dallas, Texas, USA. She received a 12-month PA fellowship and also teaches electricity, magnetism, quantum mechanics, experimental particle physics there. From August 2017 to December 2017, she was at Physical Research Laboratory, Ahmedabad, and did her internship project titled Singlet Scalar as the Inflaton and Dark Matter. From August 2016 to March 2017, she was in ITER, India, Institute for Plasma Research, Ahmedabad. There she worked on validation of nuclear reaction software tool, ACTYS, a software developed for neutron-induced activation translocation of materials. From 2013 to 2014, she was at Queen Mary University of London for postgraduate certificate in physics. She is recipient of Scholarship, International Science and Engineering Excellence Award. From July 2012 to January 2013, she was in Material Science Lab, Delhi University, and worked on thin film deposition. She did her final year project verifying time dilation by determining the muon life, mean life of muon. And she worked at Caltech and served at LIGO from June 2011 to August 2011 in the project Prototyping Adaptive Feed-Forward Seismic Noise Cancellation as 14-meter interferometer. This is a brief introduction of resource person. And hello ma'am, welcome to our college and to this webinar. Now I'd like to request the respected principal sir of our college, Dr. Surajit Bhuya, for give an opening speech. Sir, over to you.
Thank you. Good morning to all of you. On behalf of Lakhimpur Girls' College family, I welcome you all to this webinar organized by Department of Physics, Lakhimpur Girls' College. This is the third lecture of this 3 days webinar, which will be delivered by Ishwita Saikia from Southern Methodist University, Dallas, USA. And her topic will be Cosmology and Dark Matters in Introductory level. I think it will be a very interesting and helpful session for young generation. I also think she can inspire the new generations to go or work in this field and to explore and to learn the different aspects of this fascinating universe. I offer my sincere thanks to Ishwita for accepting our request and for giving her valuable time in the midst of her busy academic schedule. I thank to the Department of Physics of Lakhimpur Girls' College for organizing this. And with these few words, I would like to declare this session open. Thank you.
Thank you, sir. Thank you. Now, over to you, Ishita ma'am.
Yes, thanks a lot for the nice introduction. Okay, so let's start with the talk now, and let me start sharing the screen. Okay, so the topic is cosmology and dark matter. Actually, a very big topic, covering a lot of physics, and it's not. It's yeah. No, this is good. Okay. So as you can see, that there's a lot of topics to be covered in cosmology, and nowadays in physics, the research is very interdisciplinary. It's like we can't say like we are working only in one topic of physics, because everything is related and you need all your basic physics knowledge, whatever you're learning in BSc, everything, like even the things which you find a bit boring. Like I used to find solid state physics very boring in my undergraduate years, when I used to, like, it was really painful to study that subject. But then I realized that I need something like solid state physics, even when I'm not doing material science research, even when I'm trying to do research about the beginning of the universe and all those things, I still need to know about solid physics. So as you can see, physics is like everything is connected. And unlike other branches of science, like chemistry or biology, where you have proper divisions and you can focus everything in that particular topic. So cosmology is about the origins and evolution of the universe. And as I said, many of the recent research work is with these topics, and they're intersected with fields like particle physics, astrophysics, astronomy, and etc. But today we are going to focus on one topic, which is dark matter. Now, okay, I'm also going to try to explain in Assamese and Hindi, because it's been a long time since I've spoken either of the languages, especially with regards to my topic. And as you know, because of the pandemic, everything is like halted. It's a bad situation, and my plans to travel to India this year has been indefinitely postponed. Okay. Now, আমি যেতিয়া কিবা বস্তু আমি দেখি পাওঁ, মানে আমাৰ ওচৰত আছে দূৰত থকা বস্তু ইয়াৰ ওচৰত থকা বস্তু, যিবোৰ আমি ম্যাটাৰ বুলি আমি ক'ব পাৰোঁ, আমাৰ লাইক জেনেৰেল অভাৰঅল ৱৰ্ড। কেলে আমি আন্ধাৰটো দেখি নাপাওঁ, লাইট থাকিলে আমি দেখি পাওঁ, দুপৰীয়া দেখি পাওঁ, ইয়াত বা ইলেক্ট্ৰিকেল লাইট দেখিলে আমি দেখি পাওঁ, কাৰণ সিহঁতি লাইট দিয়ে বেচিকেলি সেইকাৰণে। নহ'লে আৰু যদি কিবা এটা বস্তু আমাৰ পিছফালেও আছে, যেনেকৈ এইটো নিউটনৰ আমাৰ ফেমাছ ষ্টৰি হয় যে এপল পৰিলে তাৰ ওপৰত, সিটো প্ৰথমে এপলটো দেখা নাছিলে, মাথাৰ ওপৰত আছিলে, তাৰপিছত লেকিন তাৰ মাথাত লেকিন পৰিলে নোচোৱাকেও, লেকিন সি ফিল কৰিলে গ্ৰেভিটি, ৰাইট? তো আমি এনেকৈ এইটো বহুত লাইক চিম্পল ৱে হয় মানে মেটাৰৰ কথা বুজিবলৈ। নাও মোৰ আজি টপিকটো ডাৰ্ক মেটাৰ অকণমান থিয়ৰী আৰম্ভ কৰিম মই ষ্টাৰ্টিঙত, লেকিন তাৰপিছত মই এক্সপেৰিমেণ্টেল ছাইডত ফ'কাছ কৰিম। তো এক্সপেৰিমেণ্টেলটো তাৰমানে সেইটো হয় কি, না এইটো এটা কোমা গেলেক্সি ক্লাষ্টাৰৰ ফটো হয়। আৰু so now all the hype and all the hot topic in physics research right now in this century is about this thing called dark matter, something called dark matter. Because I mean, you believe it or not, like we just know nearly like 4.9% of the content till now. So basically, 90% is still unknown to us, like completely unknown. I mean, we don't even know what it is made up of, what are the fundamental particles it is made up of. And this has been a long time, I mean, long, long process and long struggle by the scientists to actually find out about this remaining 95%. And so that's the thing about the night skies, that it's not all, it's like now it's all about the things which you can't see. Like when you look at the night sky, especially from like outside the city, obviously you need to go outskirts of city where there is less light pollution. You see a lot of stars, beautiful night sky. But what we are concerned right now, and what everyone is struggling with, is the things which we can't see, the black space basically between these stars. And this is a great thing for upcoming scientists, people who are interested in research, because everyone is trying to find out some way or the other, how can we learn about this? Whether they are theoretical physicists or experimental physicists, and everyone's trying different kinds of detection methods and coming up with different kinds of experiments while thinking about the economical aspects also, because all these experiments nowadays, which are all collaborations between different countries, require a huge amount of money. They're all like multi-billion US dollars, which are mostly tax money. And like one might think like, okay, fine, what will we do, like even if we find what is there in the universe, 95%, I mean, what's the use? But that's the thing. So physics has to develop first before the technology catches up and you can find the use of it. Like simple example, like if we talk about Einstein, now he came up with the most beautiful theory in the world. He came up with general theory of relativity. At that point of time, it was very theoretical. It was a very complicated mathematical formulation of physics theory, which had to do with like space time, which something which you can't even see, and it's like difficult to imagine. It's about different frames of reference of our physical world, and about the concept that speed of light is same in all frames of references. Now, at that point of time, it will look like, okay, what are we going to use that in the physical world? Like, is there going to be any use? But then later on, after many years, when technology finally caught up, basically many things are due to relativity. Your satellites, your GPS, which you use in your phone, and GPS is very important. As you know, it's not just a navigation tool for you to travel around. It's also like used by various applications in your phone and laptop. And it has use in all kinds of fields, in medicine, in biology, and everything. So that's the thing. So once we find out this invisible matter, for us, it's invisible because it doesn't emit any light. We just know that it exists. Like we do have indirect evidence. We know it exists because of the gravitational effects. Okay, so this whole thing started actually in the 1930s. This term, dark matter, it's thought that it was first used. I mean, we know he used it, Fritz Zwicky, the scientist, but maybe someone has used before that. But there's like written documentary proof that he found out a discrepancy between the observational values and the theory formulas which we have. So he did a very simple thing, which like to understand, we just need to know F is equal to ma. Basically, we need only Newtonian dynamics. We don't need Einstein's complicated relativistic theories, which we learn in our later higher physics education. Now he calculated, like he had the observed measurements of velocities of the galaxies. So this is something which the astronomers have done pedantic research work, and they have calculated these things. Now he calculated the gravitational mass in a large scale of the galaxy using your Newtonian dynamics, Weyl theorem, etc. And then he estimated the mass, also the mass which you can calculate by the luminosity of the galaxy cluster. That is by a telescope which is observing the light emitted by the galaxy. And you would expect these to be same, right? Because basically you're just calculating the mass profile of the galaxy. by two different methods. The first one is by using a theoretical Newtonian, Isaac Newton's formula of gravitation, and the other one by direct calculation of your observation through your astronomy experiments, like giant telescopes and all those things. But there was a huge difference, like a really huge, like 2 orders of magnitude difference. So that means the gravitational effect, the mass which we calculated using our gravitational theoretical formula, is showing that there is something more in the galaxy, not a bit more, a lot more in the galaxy than what we actually see through our telescopes. So this was a very big and a very surprising and discovery. And then people will be like, oh, you know what, maybe Newton was not completely correct. Maybe the theory of gravity, like, F is equal to ma, F is equal to g mm by r square, your gravitational force formulas, those things do not work in macroscopic scale, because you know how big a galaxy is, right? So they said maybe like the theory is not complete. Maybe we need a modified Newtonian dynamics theory, which will explain that, the mass calculation is wrong. I mean, this is obvious. This is very obvious that this is the obvious thing to first think about it, right? Because you will obviously believe more in the experimental result, which you have seen by a lot of astronomers all over the world. They have calculated the mass. So you would obviously believe that over a formula where you just plug in your numbers and then, compute it. But after decades of research, like this happened in the 1930s. So it's like we are now a long way from them, that time. And they have found out that there's no modified Newtonian dynamics theory which will explain such a huge difference in masses. So there's definitely something dark, something which we cannot see from our telescopes. And it's like, and this is not the only evidence. We have a lot of indirect evidence regarding dark matter. And by indirect evidence is that we have observed the universe, we have observed the night sky to look at the mass differences. What we are looking for now is direct evidence, a direct detection of dark matter. Because if dark matter exists in all these galaxies, which we can see in our observable universe, by observable universe is the part of the universe which we can observe using our telescopes and other astronomy experiments. Now, in this observable universe, if all these galaxies have so much mass, that means our galaxy also has a lot of mass, which we cannot observe from the stars and the planets. So that means the dark matter is there right now between us. Like, I mean, there might be dark matter particles which are passing through my hand. So that means we should be able to detect it on Earth. We don't need to set up an experiment in space. We will soon, hopefully, one day we'll do experiments in space. But right now we're trying to detect it on Earth. And that's the good thing nowadays, like I believe, because we are in a time historically where we have not just the technological instruments to do a collaborative experiment with different countries, but also there is relatively a lot, the world is at more peace than it was, right? I mean, we still have our own share of problems, but if we look at the scientific history, we are right now in a very sort of, I can say relative peaceful time. So these collaborations that's why we are able to do giant experiments, expensive experiments. Now we have gone underground. We have gone like deep underground, kilometers underground, to set up our experiments to detect all these unknown matter. Now, I won't concentrate on the theory part of the dark matter. That is like, is it just one kind of particle which is like filling up the universe? Or there's a group of particles? That is obviously more reasonable. So I won't concentrate on the theory or the predictions which we are doing for the particles. I'll mostly talk about what we are trying to detect or see them on Earth. Yes, so this is one of my favorite comics, Calvin and Hobbes. And this is about like the coining of the term dark matter by Zwicky. I mean, as I said, this is such a mystery. I mean, 95% is unknown, which has dark energy sector also. So shouldn't we call, something else other than dark matter? I mean, maybe after we like find about it more. Okay, so what do we know about dark matter? Now I said what we don't know. I mean, it's a mystery, right? I mean, that is well established. So we have something called a standard model of particle physics. This is like most rigorous format in which the particle physicists have written their data. You can think of it like the periodic table in chemistry. So this is giving you the summation or the history of all the fundamental particles which we have found out. Maybe there is more. Maybe we have these. So these are like families of particles, which I'm going to talk about next. So we also hope that maybe we have something similar set of particles, which we are just calling them collectively as dark matter. Now, primarily, it interacts with matter through gravity, which was obvious because that's how we first found out, right? Using a simple gravitational force formula. Now, it could interact with itself because there are particles which self-interact, and it does not move at relativistic speeds, which we will find out why. So these are just the things which we know right now. By relativistic speeds, I mean it doesn't travel with the speed of light. Okay. Now, the standard model of physics is like the most accurate model of particles, of all the fundamental particles which we know. Let's look at the first family of particles, fermions, the matter particles. So you can see 6 particles: up, charm, top, down, strange, bottom, which are quarks. And then we have leptons. Everyone's heard about the electrons, but we also have something called muons, tauons, electron neutrino, muon neutrino, and tau neutrino, in which neutrino deserves like special mention because it's a particle which has also baffled many physicists. And we have learned a lot about it, but we need to learn a lot more about it because there are theories which suggest that maybe dark matter is just some kind of a neutrino, because neutrino are neutral particles, right? So there might be some fancy neutrinos out there, more than these 3 types which we know. So that's why there's a lot of research going on with the neutrino experiment. In fact, there was one supposed to be in India, probably in South India, somewhere in Tamil Nadu. Unfortunately, due to some Indian politics, it did not go through. And so US took the opportunity to establish the next big neutrino experiment called the DUNE. But there are many labs in the world who are doing experiments with neutrinos because it's taking a long time for people to find out about neutrino because it's neutral. So that means it interacts less or weak with other things. If something interacts less, that means talks less with the environment we set up. So obviously it's going to be difficult for us to learn about it. And yes, so quarks are particles which combine into your known familiar particles, because we have heard about protons and neutrons, which make up your nucleus. So basically, protons and neutrons are not fundamental. They are made up of quarks. You have different combinations of quarks. And we have the next set of particles which actually took a lot of time for people to learn about them, the bosons, which are the force carriers. And if you have been reading scientific news, you must have recently learned that CERN, the largest I mean, journalists even gave name as God's particle, which many people don't like. I mean, even I don't know why it's God's particle, but it sounds good, so the media liked it. And there's still research going on with that force carrier because it's difficult to detect. It needed a huge collider with a lot of people, many countries spent a lot of money to detect it. And okay. So this is about a standard model of particles. These are the particles which we know about, and we will collectively call them as baryons. So cosmologists usually refer to them as baryons because these are known and we know everything about it. People have done a lot of research on it. Now let's get back to the evidence of dark matter. Now this is again a bit theory, but I will try not to spend much time on it. Okay, so as we saw, Zwickie's calculations, simple calculations, showed that individual galaxies have more mass than what we observed in the experiment. How did he conclude that? By looking at the rotational velocity profile, because from the velocity, he calculated the mass, right? So if you use your simple gravitational force formula, which is F is equal to gmm by r squared. Now your F is ma, obviously we know that, and but we also know another formula for force because these all galaxies are rotating. They are spiral galaxies or any kind of galaxy. So we can use the mv squared by r, which is the centripetal force formula. I don't want to write a bunch of equations, but I mean, even high school, like you must have learned this in your high school first and then in your undergrad about these basic gravitational waves and rotational formula. Now from these two formulas, you can calculate the velocity profile. V is equal to square root of gm by r. Now in this, the numerator g, which is the universal gravitational constant, is a constant. And the mass distribution of the galaxy, which you are going to calculate. And we have the square root of r also in the denominator. Now r is the distance from the center, which also you know because you're observing it. So you know the velocity profile is basically giving you the velocity at that particular point, velocity of the galaxy at that particular distance from the center. Now, so you know so there are 4 variables, 4 terms, and you already know 3 of them. So it's easy for you to calculate the mass profile. So this is a very simple calculation where you just plug in the numbers you've observed, and then you find out that the mass is much more than what the experiment, what your telescopes are telling you about. Okay. Now, so from this evidence, we can obviously conclude that there are some unknown particles which are present and we can't see them because they're not interacting via the electromagnetic force. Now, you might have started studying about different kinds of forces, and electromagnetic force is the force which you need to study while you're learning about light, photons, and all those things. So I hope everyone knows that. Now, so this also implies that dark matter is like not interacting with anyone, right? Because if there was some electrical signal, we would have observed it. So it's electrically neutral. We can say that. And dark matter is also non-relativistic, which is that it's not traveling in the speed of light. Because if it had been traveling in the speed of light, then it would not have been able to form clumps together. Like basically the galaxy is a clump of stuff, right, in your huge expanse of nothing. So the dark matter is present in these galaxies. Now, they wouldn't have been able to like join or clump together if they were traveling at speed of light in the early universe. Now, I think you must have heard or read everywhere, like our universe is an accelerating, expanding universe. I mean, we are not just expanding, we are accelerating. Like the expansion is increasing the speed of expansion with time. And we started with the Big Bang. Basically, we started with nothing, in a very simple way to say. Now, and we can also say that they must be stable because they're not interacting with anything much. Otherwise, they won't be so difficult to detect. So this was one type of evidence for dark matter, that is the galactic rotation dynamics and the velocity profiles. Now we're going to come into something called gravitational lensing. This is something recent, and this looks at bullet cluster galaxy. So it's actually two galaxy clusters. And as you can see in the diagram, in the picture, that there are 2 sort of concentric circles. I mean, they're not proper circles, but they are like sort of circles. So you see 2 centers. That means there are two centers of two galaxies. And the green lines are the weak lensing contours. That is, you're looking at the gravitational effect. So you can think about gravitational lensing as a study. It's again an experimental. These are all experimental indirect evidences where you're studying the gravitational effects of these galaxies. Now the thing is the center. So you can find center of these galaxies using your gravitational lensing methods. That is your gravity effects. And also you can look at the mass, the luminosity, that is the stars which are, shining. So they're luminous. So you can find two kinds of centers of masses: gravitational center mass and your luminous star center of mass. Now, technically, these should be the same center of masses. I mean, like their own center of masses. Because if there was nothing, there was no mystery in them, they should have coincided. Because the effects of gravity should be the same with the effects of what we observe. But that's not the case. We have different centers in these galaxies, so this is making your argument about this mysterious matter in the universe even stronger. And we can also again, I'm mentioning the fact that these are very stable, weakly interacting matter, because these things will eventually help us to design experiments which will be able to detect these mysterious particles. And this is one of the things which are actually difficult to explain by the infamous or famous modified gravity theory. Because these are the large structure or large scale formations which cannot be explained properly with a theory which says that Newton's gravity is not complete. Okay, so there's a lot of cosmological evidence, a lot of theory going on, which I'm not going to go into the real details because maybe we can have a separate talk about it. So this is something actually not exactly this, but yeah, this is the part of cosmology where my spouse is working in. So he's also a PhD scholar and he's working the theoretical side of this topic. So there's something interesting called the cosmic microwave background, this in short CMB is another way to see evidence of the effects that dark matter has had in the formation of a universe. So this is a very, very tricky part of cosmology because you're trying to come up with theories at the beginning of the universe, which is very difficult to experimentally prove, to create scenarios. Basically, it's difficult to give birth to a universe and see which theory works. So that's why people come up with a lot of computer programs, computer softwares to do simulations, that is to enact a world in which your theory is modeled into. And you can look at the effects and the results of the theory on these constraints and variables of your program to see how correct your theory is. Do you get a present universe? Do you get a universe which resembles the current universe which we observe? So this is where things like machine learning comes into play. And because you need an AI, you need sort of a self-learning or a self-learning computer program which will be able to simulate a universe based on your theory. Now, in the first moments after the Big Bang, which is the beginning of the universe, most of the energy in the universe was in the form of a very hot ionized plasma, right? I mean, no structures formed, nothing was there. Then, as I said, universe is expanding, not just expanding, acceleration of expansion. Now, as the universe expanded, it also cooled. So initially it was really hot, plasma, obviously it's going to be really hot. But then as it was expanding, the temperature of the universe, the small universe which we have, is also cooling down. So this cooling caused much of the plasma to clump together into hydrogen atoms, allowing leftover photons to escape the plasma and spread nearly uniformly throughout the ever-expanding universe. Now, as the universe continued to expand, these photons became more and more redshifted. That is, their frequency increased. And today, they have an average energy that corresponds to a temperature of about 2.7 kelvins. So this background, this cosmic microwave background is very uniform. Yeah, it's nearly uniform. So this is basically a remnant noise. Okay, for us it's noise because we are not trying to study the cosmic microwave background. We are trying to study the mysterious matter in the universe. But there are experiments which specifically study the cosmic microwave background. So for them it's not noise. So noise in physics can be, it's used as a word to explain the physical things which you don't need or for your particular experiment. So this is a remnant. So this is photon, this is radiation microwave background from the early universe. So that means if you are studying cosmic microwave background, the experiments, you're trying to study the universe at the beginning when it was like really young. So that's also a very interesting field of research. There are a lot of cosmic microwave experiments going on and upcoming, very ambitious experiments are getting, again, they're all collaborations, because I don't think so anything is possible if you're not collaborating with countries. Because the experiments are really big and huge. They're no longer your tabletop experiments at the time, like at the old time. Now, in the early universe, baryonic matter experienced gravitational attraction. So again, the baryonic matter is the matter which we know about, like what we saw in the standard model of particle physics. So they will, as I said, they're drawn close together and they are clumped. Okay, so the CMB is some kind of an evidence for us, like a cosmological evidence, a theoretical evidence, because dark matter did not experience all these things, right? Because if they did, then they wouldn't clump. So there are many other evidences also, which we won't be talking about, that requires a lot of time and other stuffs, a lot of maths. Okay, now, so as I said, people have been trying to find out about dark matter and wondering about it. It's a big mystery. And there are a lot of candidates. And one such promising candidate is something called WIMP, which is a weakly interacting massive particle. Now, I have actually written very basic things which I could think of. Like this slide took a long time for me to write. I mean, although it's just barely 5 sentences, because WIMP is a very big topic and for which you need to know a lot of things in cosmology. Like you need to know supersymmetry, apart from your basic standard model of physics, quantum field theory. Apart from all these things, you need additional knowledge about supersymmetry, and supersymmetry is like a lot of maths. Basically, you need to know whole of theoretical physics. Now, and so the main thing we can like think about is like, it's obviously, the name suggests it's a massive particle, and it must be because our particle colliders have not detected yet. Now, and as I said, that the things which require dark matter was that it does not travel in speed of light. That means it's non-relativistic. Now, being very massive would actually be correct for this condition. And it has to be non-baryonic. Otherwise, there's no mystery. So that means it's obviously a fundamental particle. And there are a lot of theoretical models, especially SUSY, which suggest that they're going to be electrically neutral. Now, we're talking about this particular candidate. It's because the experiment which I'm going to talk about in this talk is trying to detect such WIMP particles. Okay, so as I said, we can conclude that they should have these properties: electrically neutral, non-baryonic, that is like not, standard model, non-relativistic, not speed of light, and they are stable. They're not interacting much. And WIMP makes an excellent candidate for this. So which are trying to detect particles which are going to look like WIMP. So this was a lot of information in 13 slides. So we will have a quick review. Now, according to the models of cosmological structure formation, the luminous matter of galaxies is gravitationally bound to a more massive halo of dark matter. Now, we like to use the word halo for all the matter which we calculated and cannot see in the galaxies. So, and we're calling it massive because that's a lot of matter which is unknown. Should the dark matter of the universe consist of unidentified particles, our solar system and our planets would be passing through a flux of these dark matter particles, which constitute the dark halo of the Milky Way galaxy. So as I said, like if we are seeing it in all other galaxies, it's going to be in our galaxy also, the Milky Way galaxy. That means our solar system, we are passing through a flux of dark matter particles. So we should be able to detect them on Earth. Now, these dark matter particles could be detected directly using sensitive detectors located in underground laboratories to shield them from interactions from normal matter particles. Now, as I said, we have gone deep underground to do experiments in physics now. We have the technology, we have the collaboration and everything. And we need to be really sensitive because this is something which reacts really less with anything. It's like it weakly reacts, it's very stable. And we need to remove all the other known interactions which we know. So our detectors have to be sensitive, and we are going to call everything else which we already know and don't want to detect again as backgrounds. So backgrounds are a very important part of detecting experiments, not just in dark matter. It has to do with other particle physics experiments, neutrino experiments also. Because when you are looking at a signal which your detector has detected, you should know what that signal is, right? Whether like, is it something from a known physics model which you know how it behaves. So you create a budget, you create a background budget for your experiment. That is, you create a model and you know like how much interactions you have for you have in the experiment. This is what is, so this is actually a big part of the project, and this is where I'm actually doing my research work on. One of the things I'm working on, because the group at my university, SMU, is they are actually so there are many working groups. So they are the leaders in that particular working group. They have to create backgrounds for these experiments, and that's very important because, as I said, that's how you know that you have got a signal. Because once you calculate all the signals which your detector has detected, and then you will look at your background, right? And then you're going to remove the backgrounds. So if you collect a lot of events, by events, I mean the signals. We call them events because there's something happening inside a detector. So there's an event happening. So we see a lot of events, and then we are going to look at the background model, and we are going to remove the known events, the background. And if we have a surplus of events, that means that, okay, so these are the events which we knew will not happen, but they are happening. So this might be the unknown dark matter particle. So this is what we look for. We look for the excess of events, the extra events. Now recently, the Xenon experiment, they had a big announcement. They did a live telecast. So Xenon is the European, it's in Europe. So it's the European dark matter experiment. And these are the liquid noble gas experiments, which have become very popular now because it's very easy to use huge amounts of liquid noble gas. When I said easy, like main thing is obviously the money. You need money to do such experiments. So it's like economically very viable to construct such massive detectors. And they reported an excess of events. Like they knew like their detector should detect these events, but they detected a lot of extra events. And that is something now everyone is studying. So once they report their results, everyone is going to look into it. And then all the theorists who came up with a lot of models who predicted, this is how dark matter works. So they're going to see like whether their formulas can explain these extra events. Now, these dark matter interactions or these events, which I'm talking about, they are going to deposit a very small but measurable amount of energy in the sensitive detector. I mean, it is kind of obvious because I've been talking like how weakly interacting they are. So they're obviously, the energy they deposit in our detectors is going to be very small. So we need to build experiments which are going to be more sensitive to such small measurements. So I can sum up. So now this is the slide where we move into the most exciting part, the experimental part. I mean, it is much more I mean, it's really nice to learn about the theoretical side and look at all the different theoretical models predicted by so many brilliant minds in physics. But I guess I feel the fun is when you're able to prove who is correct and who's wrong, right? I mean, otherwise, like, there's not much fun. Yeah, so that's one of the reasons I moved from theoretical cosmology to experimental cosmology. I mean, as you have heard, I've worked in a lot of things, so finally I chose this. Now, this is something called, okay, I say cartoon because this is not what a Feynman diagram looks like. Now, Feynman is one of the greatest minds ever, and you'll study about his topics, about his work in your like postgraduate or your PhD time, because he has worked in many contributions to the quantum field theory, which is a subject which requires a lot of background knowledge. So one of the, I think the most great things about which 20 pages to just one page. So that's like some kind of a brilliant mind. Like he saw those 10 pages and he's like, oh, wait a second, you don't need to do this. You just follow these couple of rules, 5-10 rules, and then you can measure, you can like, you can compute, you can calculate the same amount in a very less time. So now these Feynman rules, which I'm talking about, they take help of something called Feynman diagrams. And so Feynman diagram is just a caricature, like just a way to write down the interaction of the particles which we're talking about. Now in this cartoon diagram, because there's a big block called new physics, because we don't know what's happening and we don't know how it will happen, or it may or may not happen. So that's for different arrows. We don't even know which side the Feynman diagram should be. It's that unknown. So we have something called chi. So if you can see my mouse, hopefully you can see my mouse. So these chi symbol, think of them as your known particles, your baryonic particles, your standard model particles. So this is what we know. We have been like spending so much time finding them, reading about it. Now if you look at the diagram from left to right, so if they interact together, there is some new physics which we don't know. There are a lot of predictions, but we don't know which is correct. And they're giving you these dark matter. So that's one way of looking, right? So if you go from left to right, the blue arrow, that's the production. So you are producing dark matter from known particles. Now that's most simple thing which you can look for. So how will you detect them in experiment forms? So this is where the colliders, the particle colliders, for example, CERN, we have a lot of upcoming new colliders. China is building a big one, and US is building them. Finally, US got a chance. So till now, Europe was the one in Switzerland. CERN was the one which has been in the big news, detected Higgs boson, largest collider particle. But it's going to be, I mean, CERN will be there, it's a lab, but the Atlas and the CMS, all the collaborations, they will be shifting gears and to look in Higgs decay, and after that, because they are reaching the energy limits of 14 TeV. So everyone's moving into new collider experiments, and US got the electron ion collider, which will be in Berkeley National Lab. So these colliders are going to collide known particles, and hopefully they're going to produce some fancy particles which we don't know about, some supersymmetry particles, and there might be dark matter because hopefully. So that's one way to go. And then there's something like you go opposite direction, like this. You're going from right to left, the red one. So that's your indirect detection. So which we observe in the universe. So that's why the evidence was called indirect, because it's happening somewhere far away from you, and you're just observing it from Earth. Now green, the direct detection, is the one which my experiment, not my experiment, the experiment I work for, the collaboration, is working on. So it thinks that the dark matter which is around us, it's going to interact with something known, a known target, known particles. And then there's going to be some new physics going on, which will give us hopefully more dark matter, some other dark matter, kind of dark matter, and some other known particle. So this is a very simple cartoon kind of Feynman diagram. Okay, so now we're going to talk about the experiment which I'm working on. So CDMS, it stands for Cryogenic Dark Matter Search. Cryogenic means it's in, the detectors are kept in really low temperatures. That is, again, to, as you will find out, to remove all the background signals and noise, which for us, which is noise, because we're not studying them. Now, this is a series of experiments, actually. So it started with CDMS 1, which was actually under Stanford University campus. So there's something called a Stanford Underground Facility, which, so basically all these experiments are underground because, as you remember, we talked about cosmic microwave background. So we're getting rid of it. So this cosmic microwave background is always present. So they penetrate the Earth also. So that's why we need to go deep underground so that we're not able to detect them. We need to detect dark matter. Then there was CDMS2, which was in Sudan mine. So that's why the convenient spots to do these experiments is old mines in US. There are a lot of mines here. It's a big country, almost like a continent, and you have a lot of old mines. So basically, someone has already done most of your work. They have dug deep underground and they have created some room for you. And you can set up experiments there now. So in Minnesota, which is like north of US, they started the CDMS2 experiment. And I mean, these were not successful in the sense, I mean, they taught us a lot of things, but we did not detect dark matter. Otherwise, this talk would be really different. And then we went to SuperCDMS. So it's the same thing. It's the same cryogenic dark matter search, but this time it's super because we have upgraded it. We have made it more sensitive. And this time we are going more underground, we're like deep underground, again in the Sudan mine. And they collected data from 2011 to 2015. Now, so these are like learning steps because we still didn't detect. And now we are in the SuperCDMS no lab collaboration. So now we have decided to go to some other mine. We're going to go more deep underground. So this time we moved to Canada, Sudbury, again, like north of Canada, below Alaska. And so they have already started construction and they're supposed to start taking data from 2020. But then because of the pandemic, everything is going to be changing. But Canada is doing really good with pandemic. So they have already actually started opening the facilities for construction and for the scientists and engineers to start working. And as you might have seen the news, people from US are not allowed. Although research is considered essential, but I don't think so this kind of research is considered essential. I mean, I was supposed to be there and then like now I'm here, but this is fine. I can be next year also. This is it's something like very nice to see because first of all, I've never gone to a mine in India. I don't think so we do any tours because here, like for them, mines are like tourist parks. So they'll have like tours, like you pay money and they're going to like, take you in the small car, show you the mine, how people used to like mine irons and other metals. So it will be really nice to go there. And the snow lab facility is really underground and it's one of the cleanest, largest clean room. I mean, you'll obviously need clean room to detect some unknown particle. Now, as I said, this is a direct detection dark matter experiment. It's direct because we are going to observe dark matter directly interacting with your known matter. And now there are some like red highlighted words because those are the words which I believe no one will know because they have like made it up for this experiment. So which we will find out. Words like electron recoil and nuclear recoil and IZIP. And as we will see, like these direct detection experiments, they measure something. So what do they measure? We are going to find out about that also. And yes, let's see. Oh yes, so the main, the oldest detectors which we used in CDMS 1, 2, and Sudan were the IZIPs. But the Snow Lab will have another kind of detectors called HVEV, high voltage detectors, along with the IZIP. We are going to use germanium and silicon both as targets for the experiment. And there's already a prototype actually, which is called CUTE. I think they did it on purpose. So it's a cryogenic underground testing facility. And that's so everyone's working on that because that's the experiment which is actually running, which is taking data. So CUTE has, it's a prototype. It's a small version of this giant experiment. It's in the same place, same underground facility, Snow Lab. So basically it's same deep underground, but it's on a smaller level. So usually all these giant experiments need prototypes, mainly because when you go for asking money, you should have a prototype running. They're like, oh, we already have something small running, so we need money to build something big. So that's one of the main reasons. But you also need them because you need to know a lot of things before you build something that massive. You have a lot of unknowns and a lot of theoretical models and things which you need to test on a small scale before you ask for a lot of money from all these people. I think like US has already spent 13 million to 19 million, and they have US dollars, and they have again dedicated more amount of, it sounds a lot, but sorry. So we're talking about, yes. So we need like prototype for many experiments, like the LIGO experiment, which finally detected the gravitational waves. That is when you must have heard in the news. They also had a prototype at Caltech before they built huge ones in Italy and Washington and Louisiana in US. And yes, so I would like to talk more about it at the end because India is part of the collaboration. They're going to call it Indigo, I guess. I don't know if things have changed, but I think the progress has stopped because I haven't seen in the Indian budget, they haven't mentioned it yet. So I hope India catches up soon because they need a detector in India or Australia. That's how they'll observe the whole observable universe, to look at the whole universe. So we're going to talk about electron recoil events, nuclear recoil events. Again, events is something which happens inside your detectors. And we talked about WIMPs, neutrons are particles which are neutral. There's something called CDMS light, which we won't go into because it's right now not, it's already done. So they already collected data and it's not running right now. Okay, so as I said, the SuperCDM Sudan experiment, which already occurred in 2012, 2015, was underground. So they actually give you tours. You can go there, pay some fees, and look at the mine. So they have a lot of experiments going on. There are neutrino experiments also in the Sudan lab, and along with dark matter experiments. And as you can see, there's a picture in the entrance of the mine. Anyone can, you don't have to be a scientist to go there. You can just go there and have fun. So it was an old Sudan mine ore, which was, and it became a lab in the early 80s. And they call it the Sudan Underground Laboratory. Now, SuperCDMS was on the 27th level, which is actually 730 meters below ground. So it's like really good. And they're going to continue all these things in Snow Lab, Canada. Okay, so as I said, they're an international collaboration. So you have a lot of institutes working in it, but you have the main institutes which take care of the main working groups of your collaboration. So we have the SLAC National Accelerator Laboratory, which is, SLAC is the Stanford National Lab. And they take care of all these cryogenic mechanics and electronics. Cryogenic is like really cold environment. You need to build a really cold environment where you put your detectors. And everyone does offline computing for the experiment. Then you next have the next national lab in US. So these are all in US. Fermilab, which is the Fermi National Accelerator Lab near Chicago. And they're mainly right now, they're working on calibrations of the detectors, future detectors. They have the Nexus project also going on, which is the next generation of detectors they're going to use in dark matter experiments. So we are also working for future detectors, although like this one is still getting constructed. And everyone's going to look for faint WIMP signals and in an environment dominated, yes, we have a lot of strong background signals. So it's really difficult to detect something that less interacting. Next, we have the Pacific Northwest National Laboratory, PNNL, again in US. And they are understanding background and the sensitivity precision. We also have a lot of US universities. We have Berkeley, we have SMU, we have actually many universities in Texas itself. And this is an international partnership with Canada, France, UK, and India. In India, the collaboration is from NISA, which is in Bhubaneswar. And then obviously we have the Canadian partners because they're spending money. It's getting built in that country. So I think they're spending part of the funding. Okay, so this is how it looks in the map. So as I said, here we have the NISA, and then we have 2 institutes in Europe and everything else in Canada and US. So these are the institutes which are in participation with the collaboration. So all experiments in physics are huge collaborations. And I think that's one of the reasons we have been able to move fast. Okay, so this again kind of a review. We're trying to find something which is massive. Basically, it's like 10 times heavier than proton. Now we know they are neutral because of the theories we saw in the beginning slides, and all the theories like are based on or like parallel. They are connected, not connected, similar with normal matter. I mean, we also have theories which are like which predict how they will react with normal matter. Now, detecting these particles would open a window into a completely unknown set of new particles. Yeah, so that's what I'm saying. We are hoping to learn about a lot of new particles. So basically, the goal of the experiment is to write a chapter in the book of physics about the nature of dark matter. So like they make grad students, like PhD students, go there and do a lot of work, which is kind of common, I guess. Okay, so Snow Lab is there's a company called Vale in Comine which takes care of like, you know, going down, reaching the, taking care of the mine facility. And it's one of the most cleanest facility underground at that level. That's because we want to get rid of the cosmic background and other radioactive decay. So we need to like, so one easiest way to remove the strong background signals is to go deep underground. And that's, we are also, as I said, it's going to be a cryogenic system because we need to have really low temperatures so that there's no kind of thermal noise and all, like due to high temperatures. And they are, like, although they are deep underground, they'll also be covered with a lot of shielding materials, different kinds of shielding materials, like complicated ones, so that we don't have outside interactions from the environment around the mine. And yes, and these detectors are arranged in towers actually. They're like not that big, so they'll like 5 towers we'll have. Okay, and as I said, now how does a detector work for any particle, be it dark matter or your baryons? They're going to deposit some kind of energy, right? Now this can happen. Now the energy deposited can be in many forms like ionization, scintillation, heat, phonons, which we'll see. So here's the part where I said I had to learn solid state physics really well again, because I did not like it in undergrad. So this is lattice phonons, so which we will talk about in the next slides. So these are the different mechanisms of how energy is collected in these materials. Then we have scintillation, then we have ionization, which is, I think ionization is the most common word out of those three. Okay, so let's talk about phonons. Now devices, okay, so these detectors, they are like sensitive to phonons. I think more easier term will be to describe it will be like very layman's term will be lattice vibrations. 1 second, I have to connect my charger. Sorry. So they are massless quantum mechanical particles, and they don't have any classical analog because I cannot say there's a similar particle which we learned in classical mechanics that looks like phonons. This phonon is you can say like an imaginary particle because we are defining a concept. Actually, we're defining a concept with this word, and this is very important for us because the crystals, there are crystals, the detector which is made up of materials. We are looking at the phonons. So basically, the CDMS experiments is using is measuring the phonons vibrations, the lattice vibrations, and also the ionization. That is like, because we have an electric field going through the detectors, there will be like electron hole pairs, like there will be electrons coming out of the particles. So this is what makes the experiment really nice because you're measuring two forms of energies. So your sensitivity is higher and you can like detect particles easier. Now for phonons, you can think, phonons is a very important concept for people who are interested in developing more advanced chips for your phone or any electronic device for your laptop, because phonons is the way to study how the heat flows in your material. So that's very important because when you are designing an electric electrical device. You need a device which works faster and better and doesn't heat up, because if it heats up, that's it. So you need to know how this heat flows through the material, and like how sound is flowing through the thing, like they're creating vibrations basically. Now imagine all these atoms and molecules inside your structure, like they're connected with springs, okay? They're not connected with springs. Imagine if they were connected with springs, because once a vibration, lattice vibration, like lattices are the points in your structure of your material. Now these points can be made up of one single atom or a molecule, a group of atoms. And now these springs will vibrate eventually, right? They'll go as a wave. So how will you measure something like this? Or how will you talk about it? How will you write it? How will you compute it? So that's why we are going to use something called phonons. Now you must have heard about photons, which is carrier, like quantum packets of light. Now, so these are quantum packets of vibrations. And as photons, they're also quantized. So if you have started quantum physics, you must have learned the basic h by lambda formula. So same thing for phonons also, where instead of c, you have v. You don't have speed of light, obviously. So it's basically just a fancy word for a particle of heat. And next, we have something called scintillation process. So this is another way, not in SuperCDM, but in other kinds of experiments, where you can basically detect the light which is ejected or which is formed in your experiment, in your detection. So there's a particle that emits light after it interacts. When I say emits light, I mean emits photons. So they can be detected using photosensitive devices. And then a detector can also, this is like really old, like basic thing, electron hole pairs. That is, so when we say hole, we mean like when the electron leaves, it gets kicked out of its place. So there's a hole. So that's why we talk about it as electron hole pairs, or we can simply say ionization in this experiment. Because as an electric field is applied, we have this kind of a cascade, which we are going to read about next when we learn about electron recoils. Okay, so as I said, we have the advantage because we're using two kinds of measurements. And as you might remember, we talked about electron recoils and nuclear recoils, because we'll have two kinds of processes happening. And we are interested in nuclear recoils. For us, electron recoils are again backgrounds, are noise. We need to get rid of them. How can we get rid of them? We need to learn everything about them how much contributions they are having in the detectors, and then get rid of them, so that we are left over with the nuclear recoils, because our candidate for dark matter is going to have a nuclear recoil detection in the detector. Okay. Now, since we don't know about a candidate much, they're going to deposit a range of energies. So we have to be careful and be considerate about the energies we are trying to detect in our detectors. Now, so to calculate these WIMP particles, we have three unknowns. That is, three unknowns we have to measure. We have interaction cross-section between the WIMP and the detector material. And then we also don't know the mass of the WIMP. We have a range, we don't know what it is. So then we also want to know the energy distribution of the WIMPs which are going to interact. Now in physics, cross-section is basically a measurement of a quantity which will tell you like how two particles are interacting under certain conditions. Because like if you imagine two billiard balls in a billiard table colliding with each other, it's easy to imagine they're colliding. Like you don't have to like think what is the probability if I strike two billiard balls head on together. That's not the case with the fundamental particles, because they are described as probabilities. You'll learn more about this in quantum mechanics. So we talk about probabilities. So that's why we come up with the term cross-section, which is actually telling you the likelihood, that's the probability of how the particles will interact. So cross-section is a very important term in these experiments, because the results are shown in terms of cross-section. Like any fancy plots which we see will have cross-section in y-axis and energy range or something in your x-axis. Okay. nuclear recoils. And then everything else, photons, electrons, they're scattering from electrons, so electron recoil. Now again and again, cosmic rays, we're avoiding them. Now, because WIMP events are so rare and the energy spectrum is unknown, and we don't have any special features about it, it is very hard to distinguish between a WIMP and the background. And like, plus we are competing with neutrons, which are neutral and more like difficult to control or study. But we know that they're going to interact only with nuclear recoil with these detectors. Now, electron recoils are easy to cut because the electrons, they interact with unknown forces. We know a lot about them, so we can like remove them very easily. So our concern basically goes to the nucleus of the detectors, the nuclear recoil, because it is very difficult to distinguish between a neutron interaction and a WIMP interaction. So we need to concentrate on a neutron background as much as possible. So this is one of the tough jobs. Like, we have to remove all the neutron interactions. Then we can see, do we have extra events, excess of events? Okay, so these detectors. And we stack them in towers inside the detector. And we define a term called yield, which will basically give you the difference between electron recoils and nuclear recoils. And so it's technically your ionization yield, but we're just going to refer it as yield. Okay, so this is a bit, I think I won't spend much time here because I wanted to explain a bit about recoil physics, because I mean, what is this recoil? Electron recoil, neutron recoil. This is actually a cascade of, we can come back to it actually if we have more time. So this is the same thing, like we need to like know the whole trajectory of the electron which are getting kicked out of the crystals of your material in the detectors so that you can cancel them. And nuclear recoil is also something like electron recoil, but it's just that there's like nucleus also involved, so it becomes a bit more complicated. And this is where like the energy is released as phonons. So that's why we need to learn about how to measure phonons in our detectors. Discrimination is what is going to help us to know that the signal which we detected is a dark matter or not. Because we know that all electron recoils are background and we have to get rid of the neutron recoils. So we saw the SuperCDM as Sudan and SNOLAB pictures. And so this is just a bunch of numbers, facts about the differences between like what upgrade is happening between the two experiments. And hopefully we start taking data next year. Yeah, this is more graphical, so you can see like the difference in sizes and all. So you need so basically you need more detectors, because if you have more materials, that means you're going to have more events, more signals, higher chances of detecting a dark matter. Okay, so this is, I'm going to skip through this. This is just more advertisement of SNOLAB, actually, like how better it is compared to the previous experiments. And as I said, there will be another kind of detector, HV high voltage, added to this, which was designed recently. Now this is technical, this is an old plot, I think it's like 2015 or something. So this is how usually the results are presented, like in any dark matter talks about, so this has like many experiments, not all, many detectors. And the different experiments like CDMS light and CDMS2 and all those things. So this is where the cross-section term is very important, because that's how, as I said, the y-axis is cross-section. That is the probability or likelihood of the known target interacting with your unknown targets. And so this is what we have so far. We have done so many experiments. We have a lot of data from CDMS experiments. As I said, the noble gas experiments have become very popular these days because they are very helpful to look at interactions in the high mass range. As I said, because liquid noble gas experiments are easy to construct. First of all, they are like cheaper to manufacture, and it's easier to have a massive amount of noble gas, liquid noble gas. So what we can do is in CDMS is that for us to have more signals, we can just add the number of these small detectors so that our target mass increases. But these are not, this is a bit difficult in the sense economically, because you need more money to build more detectors. Yes, so this comic actually sums up what's happening. So as you can see, she's like explaining how much she has done. They have done a lot of shielding, protecting the experiment from other backgrounds and everything. But does that mean that we have been able to detect dark matter? Not yet, but we are really good at not detecting it. I mean, we're finding the limits. I mean, like, okay, so this is where we don't have anything, so we have to push our energy and mass limits. Okay, so we're coming to an end. This is the last slide, concluding thoughts. So what we learned, we saw that the fields of astronomy, cosmology, they have given us a lot of evidence that there is dark matter and not some fancy gravitational theory. And then we have a worldwide collaboration to solve this puzzle. And I have also mentioned the challenges. Really, like, what are the challenges, like how we have to build our backgrounds and everything to detect the dark matter. And I think that later within the next we'll find. So this is my collaboration. So you can see my professor, Jori Kuli, and then we have assistant research professor, we have undergrads, and that's me. Any questions?
Thank you, Ishwita ma'am, for your beautiful presentation and sharing. Thank you.